video, I'm going to show you what is the spectrophotometer. Spectrophotometer is based on spectrophotometer, which in turn is based on or exploit one of the phenomena of light to measure the absorbance. And after we measure the absorbance, indirectly we will measure or calculate the concentration of the analyte that we are intended to in the sample. So first of all, after using let's take a look at the light or its phenomenon. The light, if we about to pass it through a prism, it will convert into its original color, as for example the sun of light or any source of light. These original colors, every color has its own wavelength, starting from the highest, which is the red, which is approximately 700 nanometer, reach the blue, which is 400 nanometer. So we have these colors. Now we want to know what is the wavelength. Here, what is the wavelength? Here, for example, the light went past through space through any other through all the direction. If we took any in two waves, if we took any wave, we will see how it's pass or how it's cross the space. This type of wave is called the longitudinal wave. The longitudinal wave arises as a peak and decrypt, peak and decrypt, peak and decrypt. And so, the distance from the half peak and to the previous half peak, this called is the wavelength. This wavelength varied between light colors. For example, here we have wavelength and we have another wavelength. If we are comparing this to this, we could see that is a shorter, this wavelength is shorter than this wavelength. So as you can see that the wavelength here is the distance between half peak and other half peak is much longer than this wavelength. Here we have the visible light, as we have seen. When it's convert to its original color from red to blue, as you can see that the red has a higher or longer wavelength. As you can see, you could calculate this distance is much higher or longer than this, and this is much longer than this, and so until we reach the blue, which is the shortest wavelength from the visible light, which is about 400 nanometer. Nanometer is equal to a bar, or let's see, a piece of 1 billion of the metal. Now let's head to the spectrophotometer. Spectrophotometer is using a source of light, any source of light that has, when we pass it through a slit and through a dispersion device or a prism or anything that disperses light to its own original colors, which is all this called monochromator. When we pass it through the exit slit, we are only allowing and we will adjust the wavelength through the spectrophotometer device. We are only allowing a portion of wavelength of light to pass through the sample to reach the detector. Either we allow to the green light, to the red, to the yellow, depending on the wavelength we are trying to use. Here the detector is using or detecting the light by main of photon. First light, when it cross the space or pass through the space, it's considered as it has energy as a photon, called photon. So when the photon strike the detector will convert this photon or form of energy, a photon, to a pulsive volts. So the higher intensity of light means the higher photon means the higher voltage that will fall. So this is the mechanism of, or the principle of the spectrophotometer device. Now we have another example, which is live. Here we have this source of light pass through slits and to the prism. Here this is the same voltage as the prism, but we are using here the grating only allowing a small portion of wavelength, and we adjust it. Diffraction grating. As you can see, every time we adjust the spectrophotometer through adjusting the knob that placed on the top of the spectrophotometer, we're only allowing a small portion of wavelength of color and other mean of wave of light to pass through to the sample reaching the detector. Now, why we see that intensity of this light here is higher than the intensity when it passed, or the intensity here is lower than intensity here. In our world, every sample, every elements, every molecule had its electrons has a specific wavelength, that if you strike this specific wavelength to its electrons will consume or absorb this beams of light, some of portion of this beam of light. So the electron will gain energy and will transform another to a higher level, or change in the covalent bond to be vibrating or to be rotating. So that's why when you pass it through the sample, which for example we want to calculate the ion, we have in this sample ion, and for example if the ion has a most effective wavelength at 400 nanometer, for example the blue light, or let's say here, since we have the red to orange, let's say 600 nanometer. So when it passes through this sample, it has ion, so ion will atoms and atoms will absorb more of, or much of the light, and depends, and this will reflect what? This will reflect the concentration of the ion. So a high concentration of ion here means the lower intensity of the light that will pass through it. So this is how indirectly we will calculate the concentration. This portion of light is called the transmittance, light that transmitted through the sample. Here we have the portion of absorbance, means the light absorbed by the analyte or the molecule we have here. So this is the spectrophotometer. Now, how could the light, or how could the spectrophotometer calculate the absorbance? First of all, the spectrophotometer is manufactured, or detector manufactured to use this formula or this law, as you can see, the transmittance. We could calculate the transmittance or the spectrophotometer using this formula, which is the P over P 0. Here means the P, or P this light, or the transmitted light over the original light. So here we have this light, this portion of light is the transmitted light over, or divided by this light. So for sure, of course, this the intensity of this light will be lower than this intensity. Now that means the result will be lower than 1. So after we get the transmittance, we get a percentage of the transmittance. We will just multiply it by 100, and from this we got the transmittance. Now this will not accurately calculate the concentration of the light here. We want to know the absorbance. The amount of absorbing light is directly reflected to the directly proportional to the amount of analyte here. The higher light means the much absorbance here before. So how could we calculate the absorbance? When we adjust the device to this absorbance, or when we adjust the to the absorbance, so the device will automatically use this another formula of absorbance in regard to this transmittance. Now this will be kept in memory. So the absorbance, the device will use this transmittance to get this absorbance when we switch it to the absorbance. The absorbance law is constant as the log 10 for transmittance of the light, the intensity of the transmitted light over the intensity of the original light. So in other means, we have the reverse condition here. We have this light, or this intensity of light is divided by over this portion of light, or low intensity of light. So because of this, you could use this, but rather reflect it, so it will be 1 over a transmittance. 1 over transmittance, and since we want to use a percentage of transmittance, not just with transmittance, so we multiply it by t. So why we use log 10? The condition here is that one fold in one change for one change in transmittance or absorbance mean 10 change in the other. So for example, if we have one change in absorbance means 100 100, so we have 0 and we will have 100, means 10 fold have changed. So another mean, if we say that to which level we should raise the 10, log means to which level we should raise this number to get this number. So to which level we should raise the 10 to create 100. If we calculate it, it's 10 of multiplied by 10, we will get that. So it's a power of 2. So 10 to the 2, we will get the 100. So we have 2 here, and so we will get this formula ultimately, or at the end. So the device, when we calculate the transmittance, will use this formula. If we adjust the device or switch it to the absorbance, it will calculate this formula by using the result from this first formula. Now, even though we will not get the transmittance, or even if we calculate the absorbance of the following analyte, we will not get the concentration directly, but we need another sample, which is called the standard, that it's already its concentration was already calculated. When it's already calculated, and we measure the absorbance of this, and we measure the absorbance of this sample, we could plot it through a curve or a histogram, and by using doing a cross multiplication, we will have only one unknown a concentration, and we will get this from we get the sample from the standard. Now you could ask if we only could calculate the concentration from known concentration, then the standard, how could they calculate the concentration of it if there was nothing before it, or how could they calculate the concentration of it if it's all another also require another sample, which also needs must its concentration must be calculated. There's another formula it's used to calculate the absorbance, which says that the absorbance is equal to molar absorptivity its molar absorptivity, which is a constant. Every molecule has its own molar absorptivity, and V, which resemble the path for which the light will pass through it. Here resemble the cuvette, or the tube that is placed in the spectrophotometer of light. C is the concentration. Now, if they calculate the, for example, if we have a standard, how could they calculate the standard? First, well, the concentration of the standard. First, they measure the absorbance. For example, they know the absorptivity by other law. B is the known is the distance. C, they could easily calculate it by this, or they could, if we have, for example, if we also have this noun, C is calculated by unknown. For example, C is calculated by using by any experimental manual experiment. For example, measuring the C is measuring the weight over the volume. Weight over the volume, we could get the concentration. So they could just easily calculate the weight of the sample before dissolving it in the solvent, and calculate the volume of the solvent, and dividing the weight of the analyte over the volume of the solvent, and then you could get the concentration. From this you could get the absorptivity, or if they could just directly know the concentration, then we have the absorbance, and the concentration is known or calculated for the standard, so we could use it to calculate the concentration of the sample. So after now we could use this formula as we know it. for example, we have the sample. Let's say we don't know the concentration, C, over the absorption. Let's say the absorption is 70, is equal to the concentration of the standard, let's say 50, over, let's say the absorbance is 80. So if we do a cross multiplication, we will get C, which is the concentration of the sample we want to know, is equal to 70 divided by 80 multiplied by 50. This is most recurrent formula. We could use it always. Must use it after the end of the reading of the spectrophotometer, and from this formula we could calculate the concentration of the sample by dividing the absorbance of standard of a sample times the concentration of the sample, or the concentration, sorry, of the standard, and from this we could get the concentration. And here is the example, or is how we could calculate the concentration of the sample. Okay, so let's start with the procedure of, or how to read the spectrophotometer. As we say, one, we have the spectrophotometer. Let's say, for example, take the measurement at 420 nanometers. Here we are adjusting the node to reach the specific nanometer, which never means by changing this to be in this direction, for example, this what will happen, and in the spectrophotometer inside, we change it. Now we must now what? Change the now what we must have is that we must tell the detector, first of all, this must be closed. The slit is closed when there is no sample is in place. When there's no sample in place, it means there's no light will reach the detector. So what we are going to do that first is we tell the detector to ignore all the light, not the light of this. There's no light here because there's a dark here inside. But at the same time, there's also some light may could reflect or pass through this, or there's invisible light, or let's say lower and the higher than nanometer than the invisible light. For example, X-ray, gamma, or ultraviolet could reach the chamber here, passing through, or could let's say piercing through the walls onto the chamber here. So we are going to tell the detector to ignore the light to it. So in any light that is not rather than this will be ignored, any radiation or any beam. So when we adjust it to the 0, means that it will consider there's no light, means consider there's no light, or it's completely dark here. So any light that comes, it will consider it as a 0. Now we open, after we open the sample compartment or the chamber, when we just put the blank solution cuvette, here something must be told. They will put the blank. Here something must be told, that what is the fundamental, or what is the benefit of the blank? Blank, it's a solution that has all the components of the incoming sample, or the sample that we want to measure, except the analytes that we are going to measure. For example, if we have two, if we are trying to measure the protein inside a serum or inside a plasma, what should we do? We must do place a blank which has all the component of the blood or the plasma except the protein. So we will, when we place it here, we will ignore all the absorption that happen not by the protein, since there's no protein but in the blank, but all by other elements in the or molecules in the tube. So there will be, so it will be ignored. So then absorbance by other thing rather than the analyte we want to measure will be ignored. So there will be no the absorbance will not be affected, because if we didn't do this and directly added the sample, there will be no absorbance not only by the element we are trying to measure, but by other element in the blood. So this will raise the absorbance, which another mean reflects the will give a error or raise the concentration error erroneously or wrongfully, will raise the absorbance, which is not which we should take. We should not use distilled water. Distilled water doesn't have the component of plasma. We should not consider distilled water as a blank, because it's just a H2O, just a water and some minerals, but not having, for example, the plasma has bilirubin, globulins, and bromines, and have many cytokines, many kind of other things, while the water doesn't have most of the component of the plasma. So it will not, if we zero, we are about to zero through the by the water or the distilled water. There's still many component of the blood or the plasma will not be ignored and will give a raise in absorption as a plus to the absorption by the electrolyte we want to use, because there are many elements that have the same wavelength, for example. Now we after we just put the blank, there is just like a button that will instantly open the slit. When we open the slit here, the light will or the light that has the specific wavelength will pass through the sample through the detector. As you can see, when he just add the after he just made the absorbance or transmittance 0, as you can see. When you just open the chamber, there is another light will come to and show the absorbance or transmittance is raised a little. And we after we put the cuvette or the tube here, the chamber, it will press the button, and so the light that here will pass through. As you could see the reflect and change in the transmittance. This means that the entire light now is the slit is open, and the light of the specific wavelength is passed through and reach the detector. Now what should we do now? We want to raise the transmittance to 100. Okay, so why we should do this? We should do this to consider that this light that passed through the passed through the sample, some is absorbed, but the rest passed or transmitted through and this detector. This is considered as the as a transmittance of 100, which means that the light is as original light as this. This is considered as 100 light, 100% light. So all the light is passed through, ignoring the fact that there is some absorbance happened here, but we want to ignore it and consider the light that passed through as considered as this original light. So by this step, we got rid from the absorbance that happened by other components in the blank or by the sample we are trying to use. Next. After we zero this calibration, we must take the cuvette out. Here we place our sample, which has the N level we are trying to measure. Now we want here the device is using this formula, as I said to you before. It's using this formula. This formula to calculate the transmittance. Now we're trying to tell the device to use this formula because this will help us to get the concentration. Well, we could just keep it on the transmittance and using this formula manually and get these absorbers, but this will require a long time since we have a lot of things on this code we have to us. So we are going to tell the device to use the absorbance. Right, that is absorbance, and from the previous transmittance, as we said, which is 93, we will just use it in the absorbance log to get the absorbance, which is 0.32. And by this we have the we get the absorbance. After we get the absorbance, and we add we add first second the standard. We now we get the absorbance of the standard, and we know the concentration of the standard. Here we could just apply a histogram and plot it, and then we get the already get the absorbance of the sample. We could compare it to it and to the standard, and we have only this concentration, which is unknown, and by using the formula as we stated before, we could get this formula, as we said, uh, multiply, compare this by this, and do a cross product, let's say, cross multiply, and we'll get the concentration. And here, this is the